Hello, space fans! Welcome to the fourth and final episode of our Conversations on Dark Matter with Katie Mack. And, of course, joining me is Katie Mack. How are you doing tonight, Katie? Tomorrow
Hello.
evening. How are you tomorrow evening?
Yes. I'm having a very nice Saturday evening.
Nice.
How are you? How's the past?
I'm having a very beginning to my Saturday morning. It is midnight here in Los Angeles, and it's balmy and dry. We need rain badly, but that happens when you have a drought. But oh well, what can you do? Drink more water is what you
Yeah.
do. So I'm going to do that. And
Okay.
so what we're going to do here real quick, since this is our final episode on this series, is we're going to do a quick overview of the first three. I know that we have been posting out all over the internet the links of the first three, and I'll make sure to put them on the YouTube comments and Twitter and the event page. I know it's in the event page here on Google+. But let's go over real quick just a brief summary on what we have talked about so far about what dark matter is. So we know
Right.
it's the majority of the mass in the universe, but it doesn't interact with light. Is that right?
Yeah. So dark matter is a kind of matter that is it has mass, so it's matter. So it interacts with gravity, but it doesn't seem to interact with light, and so it's invisible. Not only is it invisible, but it's untouchable, because when you touch things, you're using electromagnetism and repulsion to touch things, and dark matter doesn't seem to do that. So whatever it is, it pervades the galaxy and all the other galaxies, and it sort of forms the backbone of the cosmic web, and it holds things together in space, and it keeps things from flying off, keeps galaxies from flying apart. But we can't see it. We can only see the effects it has on luminous matter, like stars and gas and galaxies and things like that.
Right. So that's when we see things like the rotation rates of galaxies or gravitational lensing. So we're actually seeing the effects that it has on space-time, and the light actually warps with the space-time itself. So light's still going in a straight line, but what it's going through is actually curved, and so it appears to be lensed. That still
So
blows my mind. Still does.
Yeah. We use gravitational lensing for a lot of different things, but one of the things that gravitational lensing does is it can weigh massive objects in the universe, and so you can find out what the total mass of something is, and then you look at the mass of all the things you can actually see, and you find out the total mass is many times the mass of the things you can see, so you know there's something extra there, and that's dark matter.
Right.
But we don't know what it's made of yet.
Not yet.
We think it's some kind of subatomic particle, some kind of new particle that doesn't fit in the standard model of particle physics. And we're trying to figure out what that is. So we talked a little bit, I guess, about direct detection, where we wait for a particle to come into a detector underground and bump into something, and we look for that recoil energy. And I think we may have talked a little bit about indirect detection, which I guess we'll talk about a little bit more today.
Yeah, we will talk
as an intro
more
to
today.
Other stuff.
And we talked about the bullet cluster and that it's not modified Newtonian dynamics. And honestly, like everything is here on this YouTube channel. So if you're seeing this either live or in the future, this recorded, since it is 3 a.m. Eastern. Good morning to all of our friends in the UK and throughout Europe and Africa, and good evening as well throughout the rest of the world. But so that is going to be there, and I guess, well, right before we get into it, I want to make sure everybody knows how they can get a hold of us. So I do have the Q&A app up and running. You can activate that either on YouTube or you can activate that on Google+. So on the bottom left on YouTube, you should be able to see a little button that you can click it, and it opens up a new experience where you're still able to see us, but on the right-hand side, you'll be able to see a place where you can ask us questions, and also we might be able to showcase some links. As you can see down here, I am at Scientific Scott on Twitter, and Katie is at AstroKatie on Twitter. So we both have, or at least I have Twitter up, I think Katie always has Twitter up. So, Katie,
I actually use it. I usually hide it while we're talking because it's too distracting.
Okay,
but,
well, I'll keep it
I'll
open.
see if you ask questions on the YouTube thing. I'll see. Okay.
I'm seeing lots of retweets, so thank you everyone for spreading the word. I'm seeing our viewers rank up right now, and then I'll try to also check YouTube for comments as well to be able to do that. So, as we're going, because we're also going to get into some of your research. Where do we start? I think indirect detection is how we get into your research.
Yeah. Yeah, so the stuff I work on is how dark matter annihilation or other kinds of dark matter particle interactions affect the first stars and galaxies in the universe. And if we talk about indirect detection first, it's some of the same processes. So just to sort of review what indirect detection is, so most of the theories about dark matter are that there's some kind of particle that's its own antiparticle.
Mm-hmm.
And so these two dark matter particles, if they come together, if it's like a sort of direct enough hit, then they can annihilate with each other, just like an electron and a positron can annihilate and make gamma rays. A dark matter particle can annihilate with another dark matter particle and make some high energy particles. And some of those high energy particles might themselves produce gamma rays that we can see in the sky. And so this is one of the ways that people look for signs of dark matter, is by looking for sort of bright spots in the sky where there's a high concentration of dark matter, and because of that there's a lot of gamma rays or a lot of cosmic rays or something like that coming from that bit of the sky. So I think you have a picture of what that could look like based on some simulations.
So we were looking over this image earlier. What exactly are we looking at here? So I'm going to switch that over to that screen here.
Yeah, so this is a picture of a simulation of what the sky would look like in gamma rays if all the little clumps of dark matter around us had annihilation happening in them. And what you can see here, this image it's the whole sky but like stretched out to an oval projection.
Mm-hmm.
What you can see is in the center, where there's that really dark big blue spot, that's the galactic center. And that would be the strongest signal of gamma rays in this model, because you have the most dark matter and it's very dense in the galactic center, and so you get this really strong signal. So even though these collisions would be really, really rare, even though these annihilations would happen really, really rarely, there's so much dark matter in the galactic center that you would get a much bigger signal than in other parts of the sky. And all the little dots around there, all those little dots are little clumps of dark matter.
So what's over here on the sides then? So are these like the Magellanic Clouds?
Yeah, I think those might be the Magellanic Clouds, or just other like satellite galaxies, little dwarf galaxies.
Okay.
So anytime you have, so some of the, probably the ones on the right are Magellanic Clouds. I'm not really sure.
Okay.
But whatever, they're just little dwarf galaxies that are nearby that are clumps that have clumps of dark matter in them. Mm-hmm. And a lot of this is based on sort of modeling. So all those little specks, we don't actually know that all of those little specks are real dark matter concentrations, but we expect that there should be concentrations of dark matter at those kinds of scales.
Okay.
And so this is the kind of thing you would see if dark matter were annihilating and producing particles that produce gamma rays. They shouldn't produce gamma rays directly because that would imply an interaction with the electromagnetic force, which doesn't happen. So they might produce something else that turns into gamma rays. So that's one of the ways that we look for dark matter nearby. And there's been some really interesting results recently where people think they might have seen something that could be dark matter annihilation in the sky. So one of them, one of the most recent ones, is a signal in the galactic center where they see more gamma rays coming from the galactic center than they expect from modeling star formation and pulsars and all the things that we know about that are happening in the galactic center. And so there's like a little dot, a little sort of blob of gamma rays. I think you have a picture of that somewhere.
Sorry, I was tweeting. Hey,
Oh,
Twitter.
okay.
Yeah, I can multitask. So here we go. This is
Yeah.
that image. Let me actually make it so you
Yeah.
can see
Yeah.
it, and I'll get back to typing without
Okay.
typing to everyone's ear.
Okay. So this is a projection where you can see the whole galaxy as that like yellow stripe across the center, and there's a zoom in kind of thing, and they're two different images. But anyway, the little purple image to the right with the red spot in the center, that's a picture of the excess gamma rays that this group sees in their observations. They're using the Fermi telescope, which is a gamma ray telescope in orbit around the Earth. And so they see these excess gamma rays, and so a lot of people have been really excited about this result because there's a sort of simple model of dark matter that can produce gamma rays in basically that configuration. But it's complicated because the galactic center is a really messy place. There's a lot of gas, there's a lot of dust, there's a lot of stars. There's stars forming actively in the galactic center. There's pulsars. There's a supermassive black hole doing all sorts of things. And so there's just a lot going on in the galactic center. And so figuring out that the only explanation for that excess gamma rays is dark matter annihilation is really difficult. It's really hard to rule out other like more traditional sources of radiation, because all we see is some radiation.
Right.
So it's kind of unclear at the moment if this is a real signal of dark matter annihilation or if it's something else. But we're still looking, and I think one of the things that we need to do in order to figure this out is look at signals like that, not just in sort of one wavelength, not just look in gamma rays, but also see what the signal would be in X-rays, or see what you would see in radio, or look at it with all the different wavelengths and try and find a consistent picture of what the dark matter would do to the surroundings and what you would see at different wavelengths and how it would heat up the gas and how it would put out, infrared radiation, all sorts of things like that.
Right.
So, this is one of the things that people are working on. But what I'm interested in specifically is if dark matter is annihilating or doing some other kind of particle physics like decaying or interacting with regular particles in some interesting way, what would that do to the first stars and galaxies in the universe? And basically the idea is as the first stars and galaxies are forming in the universe, you have a clump of dark matter and you have gas in that clump of dark matter, and the gas is falling together in the same place as the dark matter and forming, stars and collapsing via gravity and cooling down and then getting really dense, and then it heats up and becomes a star. And then you have lots of these, and they become a galaxy, and all this stuff happens, right? But if that's all happening, and this is all happening in clumps of dark matter where annihilation is also happening, then you have a little sort of heat source inside that object, and that can change how the stars and galaxies form. So the reason to look in the early universe, to look at the first stars and galaxies, is that the chemistry is fairly simple. You have hydrogen and helium, and the other elements have kind of not really been created yet, because
which
higher elements are created in stars and in supernovae.
Right.
Yeah.
Which we've talked about before,
simple,
so check out that one on supernovae.
Yeah. And so the chemistry is kind of simple, and that also makes it harder to cool down the gas, which means that putting a little bit of heat into the gas has a bigger effect. And so, there could be a bigger effect just based on that, but then also there aren't a lot of other stars and galaxies around to make things really complicated, like the way things are complicated in the galactic center. You have a really fairly simple universe, and if you're throwing a bunch of energy into that through dark matter annihilation, it's kind of a little more obvious than it would be in the local universe. So do you have that picture of the universe timeline that I showed you earlier?
Yeah, so let me pull that up here and try to zoom and enhance real quick. Make it look a little bit more appealing for our viewers as it's going up. Here we go.
Okay.
Yeah. So everything
Okay.
here on the left, we're looking at the inflation Big Bang period, and
Yeah.
here
Yeah.
is the cosmic background radiation, the CMBR.
Which we will talk about next time.
Next time, so tune in
Yeah.
later. In 2 weeks, we will
Yeah.
be getting into the CMB.
Yeah, so just because we're finishing our dark matter series doesn't mean we're going to stop talking. We're going to go on to new subjects, and the next one will be the cosmology background. So
Yes.
that'll be fun. You should hang out for that. Okay, so this is like this epoch, the cosmic microwave background epoch. That's like when the primordial fireball was happening. Basically, the whole universe was in a hot dense state.
Mm-hmm.
Okay, this is like in the Big Bang Theory TV show.
Oh no, no, sing it, please.
I'm not going to sing it. No,
Oh, come
no,
on.
sorry, no, no. This is the internet. The internet does not need to hear me sing. I'm sorry. It's just not going to happen. But anyway,
I think if we start a Twitter thing about this to get
no.
Kate, all right, everyone, tweet at Katie if you want her to sing the Big Bang Theory song.
No.
Okay, I might.
Anyway, yeah. Anyway, so the whole universe was in a hot dead state nearly 14 billion years ago, and this was the primordial fireball, and this was where the cosmic microwave background came from.
Right.
And then once that started to cool down, then the universe was basically mostly hydrogen gas, a little bit of helium, and it was just becoming like cooler, and it was neutral gas after the microwave background. The electrons and protons have come together. They're these neutral atoms. So the hydrogen atom that's neutral is an electron and proton together. If the electron and proton are apart, that's ionized hydrogen.
Mm-hmm.
So we had neutral hydrogen. It was just sitting there. There were little like overdensities in different parts of the universe. So some part over here was a little bit denser than a part over here, and so then matter would kind of move toward that dense part, and so you had this kind of slow gravitational collapse. Things are coming together, and so for a long time, a few million years, several hundred million years,
Right.
you have what's known as the cosmic dark ages, and this is the time when the universe was cold and dark and dense, and these little overdensities are starting to come together and form the first seeds of stars and galaxies.
So before we go any further, I want to see, because we're seeing T, obviously is time, so we're talking a little bit less than 100 to 270 million years, but then we're talking Z here, so we're seeing Z is greater than 15 to 30. What do we mean by that in astronomy and cosmology? What do we mean by Z?
So Z is redshift, and redshift, we've talked about redshift before at some point. But redshift is a measure of, basically it's how far back in time you're looking and how far away you're looking. So what it is the universe is expanding. The universe has been expanding since the Big Bang, and because the universe is expanding, things are moving away from us. Things are moving away from everything in the universe. Every part of the universe you're in, you see everything moving away from you. And because the universe is expanding sort of uniformly, things that are farther away are moving away faster than things that are nearby. So it's like if you take a sheet of rubber and you have sort of two spots close together and another spot further apart, and you stretch that whole thing uniformly, the little spots will move apart a little bit, and the other ones will move apart quite a lot. Right. So the farther apart things are, the faster they're moving apart. And so when we look out into the universe, the things that are moving away from us fastest are the things that are farthest away from us. And so we can measure that by looking at the redshift of light, which is a Doppler shift of light. So a Doppler shift is like when a race car goes by you and it goes zoom. The change in pitch going down is because when something is moving away from you, the sound it makes goes down in pitch. And same thing happens with light. When something is emitting light and it moves away from you, the light becomes redder. It goes to the red part of the spectrum. It goes to the longer wavelength part of the spectrum. In the case of...
Now, does this have to deal with because at first we're thinking, let me turn off my screen share.
Okay.
We know that light in a vacuum has this constant speed, this constant velocity around 300,000 kilometers per second. But we're talking now about the expansion of space-time itself. Is that what's causing this redshifting? It's not necessarily that it's slowing down, but that it has more distance to go because there's now more space for it to go through, and so it's actually almost physically spreading out those wavelengths. Is that about right?
Yeah. It's kind of, you can think of it as like stretching the light to longer wavelengths. Yeah. So things that are in visible light in the visible part of the spectrum go to the redder part of the visible spectrum. If you go far enough away, then you're getting into like radio wavelengths, things like that. So the reason the cosmic microwave background is in the microwave part of the spectrum is because it's very, very far away, and it's been stretched out. It's very far away, it's very far back in time. These two things are the same when you're thinking about astronomy, because the farther away something is, the longer ago the light had to leave it to get to you.
Right.
So every time you look at something farther away, you're looking at something farther back in time. So that's what redshift is.
Okay.
And so so when you look at something that's redshifted, where the universe was twice as big, or the universe has expanded by a factor of 2 since that thing happened, then that's redshift 1, I believe. So something like that. So redshift measures like how much the universe has expanded since that thing happened.
Okay.
So yeah, so the time we're talking about, the cosmic dark ages, redshift 15 to 30, it's a long time ago. The universe was much smaller, denser, and not much had happened yet. And then something happens called reionization, which is that the first stars and galaxies form. They make little bubbles of ionized gas around themselves because they're putting out energy into the gas, and it ionizes. And then you have these bubbles of ionized gas, and those expand and overlap, and then you have an ionized universe. And that's what we live in today. Right now, if you go out into the universe, far away from all the stars and galaxies, and you look at the neutral, and you look at the hydrogen around you, it's going to be mostly ionized. So the epoch of the universe that I'm interested in terms of what dark matter is doing to stuff, is when during that neutral time, or around the time the first stars and galaxies are forming, because there's so little else going on that dark matter annihilation or some other kind of dark matter physics could be really important and could change how the first stars form. And then you can look at in radio telescopes and try and observe the gas that these first stars are forming in and see the effects on that. And that it would be a long story to go into exactly how that all works, but anyway, that's kind of how I'm interested in observing this stuff. So I don't do the observing, I just do the modeling, and then somebody else observes it.
You're like, oh yeah, please observe that for me. I've got some things
I'm a theorist. You don't want me next to the telescope.
Because something might break. So essentially you're looking so far back in time that when we're talking about the neutral IGM, we're talking very, very minuscule fractions of time compared to the age of the universe. We're at almost 14 billion years now, and you're talking about time periods less than 100 million years old.
Well, around a billion years old.
Around a billion.
Okay. A billion or a little less, yeah.
Okay. So still a really, really young universe, and so you're like time traveling as well. And this is why I still think that you and Alan both have a TARDIS down there that I'm not aware of.
I mean, he's the Doctor Who fanatic.
He is. He keeps telling me that he sent me a TARDIS somewhere in my flat, and I've not found it because of the chameleon drive, and it makes me sad. So
if people don't know who we're talking about my colleague Alan Duffy, who is an astronomer at Swinburne University here in Melbourne, and he and I have our own YouTube show called Pint in the Sky. And we haven't put out any episodes in a while, but you should check them out if you feel like it.
But there might be some in the future.
There might be some in the future. We're scheming. Yes.
there are
Yes.
schemes in the plan. So,
Yeah.
back from dropping spoilers on future plans here. So you do a lot of work on the very early universe, and
Mhm.
but what exactly are you studying? So you're doing modeling.
Yeah.
You're doing computer modeling
Yeah.
inside, indoors. You are not doing anything near radio telescopes or microwave telescopes or anything like that. You are
No.
doing computer modeling. So what really goes into that, and how does one do research when you're doing only computer simulations? I know many people think,
Yeah.
oh, you just put things in and you can make whatever up. How does a theorist actually work, and what have
Right.
you been able to find with your work?
Well, so the kind of stuff I do is I put in the equations of how dark matter annihilates based on its density and based on the mass of the particle and stuff like that.
Hmm.
And I work out how much energy it would produce, and then working with my grad student, we put that information into some codes that calculate what the annihilation products would be, so like what kind of particles would be produced in this annihilation event, and then we put that into another code that works out if those particles are produced, where does the energy go? So if you have a ball of gas and you're annihilating in the center of this ball of gas, and then you're creating energetic particles and photons and stuff, how do those interact with the gas, and does it heat up the gas? Does it ionize the gas? Does
Right.
it push the gas out of the dark matter blob, like what's happening. And so there's a bunch of little codes that we sort of connect together. And then we work out sort of like the large scale effects. So we take averages of how much dark matter there is in the universe and all the different kinds of objects and how much energy is being produced by those things. So it's a lot of putting equations into the computer model and sort of turning crank, and then it's a lot of
Is
sort
there
of
actual
analytical
crank?
calculations.
Please
Is
tell
there
me there's
actual
an
crank?
actual crank.
No, sorry.
Is there like a
Sorry.
switch?
It's just an
It'll go
expression.
ka-chunk.
You mostly just press enter.
Oh.
Yeah,
Well,
sorry.
I just asked
Sometimes you have
because.
to compile things.
Oh, okay. Well, I was just up at the Mount Wilson Observatory, and they still have
Yeah.
the DC switches where you
Cool.
power
Yeah.
on by, like, the Frankenstein movie
Yeah,
switches,
yeah,
right?
yeah.
They still
No, that's
have
pretty
those,
cool.
and it's awesome. Because you see the spark and
Yeah.
everything fly out. So, I just
Yeah.
you should have your grad student build you one just to hit enter, just to.
I'd rather she work on the computer modeling, really.
Okay. Well,
Instead
in
of
undergrad, maybe have an REU.
Yeah, I could get like a high school student or something.
There you go. All right.
Anyway, so she's working on that. We're working with some particle physicists, including Professor Elisabetta Barberio, who is at the University of Melbourne also. She's a particle physicist, and she works with stuff like the Large Hadron Collider.
Mhm.
And so she's doing some of the particle physics part of the project, and her master's student, Cassandra Avram, is also working on that. So we've got a good team going for this particular part of the project. And then I'm also talking with some other people about doing sort of much more detailed large-scale simulations for figuring out things like how much molecular hydrogen versus atomic hydrogen is being made and stuff like that. So there's a lot of little parts to this project, and I'm working with a bunch of different people, and it's really interesting so far. I mean, I think there are a lot of different ways that dark matter can affect the first stars and galaxies, and I'm trying to kind of explore all of those and put them together into one kind of big picture.
Well, because it seems like if we can figure out what was going on in the early universe with the way that dark matter interacts, it might give us some more insight in how it's working now. Is that what we're hoping to do, or?
Sure, that's part of it, and also, but I think the big part is that it'll give us some idea of what we expect to see in future observations with things like the Square Kilometre Array, which is this massive radio telescope array that's being built in Australia and South Africa, and that's designed partially to look at this epoch of reionization and to find out how the first stars and galaxies lit up the universe, basically. And if those first stars and galaxies are being affected by dark matter annihilation, that's going to change what we see in that telescope. And we might learn something about dark matter. We might also just learn something about how the first stars and galaxies worked. So doing these simulations is really important before you do a big observation so that you can test your theories by comparing them to what you calculate you should see.
Got it. I remember when I first met you and started talking with you about what you do, and I found it so interesting that you're doing this research on dark matter in the early universe, and that you're also working with those with the Large Hadron Collider, getting into particle physics, and finding out how those worlds, which typically you wouldn't think, you're looking back into the very early moments of our universe, why would we be doing anything with the Large Hadron Collider and particle colliders? But you're saying that there is this fusion between them on how we can better understand, because we're looking now at more fundamental particles.
Yeah. So
that's what times, yeah.
Yeah. I mean, the Large Hadron Collider, part of the reason you have it is to simulate the conditions of a time even before the first stars and galaxies, when the universe was still in that sort of cosmic fireball state, when you had much higher energies throughout the whole universe, and so the conditions were very different, and you expect to see very different physics going on. And so the Large Hadron Collider, doing those collisions, is designed to simulate that and to see what happened at really high energies really early in the universe, and what does that tell us about how all of particle physics fits together. And it's kind of, and I used to work in, so you kept saying early universe, and I chuckle a little bit at that because I used to work in actual early universe physics. I still do a little bit of that. So the stuff I work on now, I would call high redshift astrophysics and cosmology and particle astrophysics and particle cosmology and astroparticle physics. There's a lot of different ways to talk about it. But I've done some project on actual early universe physics where I've been thinking about the epoch of inflation, cosmic inflation. Oh,
so we're talking moments after.
Really early.
Right.
10 to the minus 35 seconds, that kind of time. And so I've done some projects on that, and I've done some projects on axions, which are another dark matter candidate, which were produced, again, this very, very early time, maybe even before the epoch of inflation. So, really early universe physics, early particle stuff. But my usual thing is I like to try to connect, fundamental particle physics with stuff we can see in the sky. So, I work on figuring out what the fundamental particle physics models would say would be happening, and then I talk to the astronomers and say, well, what could you see if this were happening? And I try and figure out what new telescopes could see, what kinds of observations we need to make to test these theories. But I don't do the theories. I don't do the observations themselves, and I don't come up with new fundamental theories. I'm kind of trying to bring it all together.
Got it. That's awesome. Well, we're running out of time real quick, but there is one question that I think that we can actually address. There's a couple. There's another one here which we won't have time because it's going to require me to download a PDF and try to figure out. So it looks like someone linked us to a paper, and I'm not going to read a paper on air. But Adam Synergy here asks, load this up here in the Q&A app. So is Katie's interest in the early universe, so I guess maybe we already differentiated between that, similar to Catherine Fries's and Doug Spolyar's work on dark stars, in quotes, heating the early universe and helping to form the first stars?
Yeah. So I know Katie Fries very well. She just wrote a book about dark matter, actually, that you guys should check out. It's called, I don't remember what it's called. A Cosmic Cocktail is so a Cosmic Cocktail is the title. The subtitle is something like some number of parts dark matter. I don't remember, but it's apparently a really good book. I haven't read it yet myself, but I've heard good things. And I know Katie Fries very well. There aren't very many Katies working in dark matter, so we're chums. We go out dancing when we're at the same conferences and stuff.
Nice. So Katie's unite.
Yeah. So anyway, so Katie and Doug Spolyar and some other people have been working on stuff to do with dark stars, which is an idea where you could, in theory, when the dark matter is annihilating these early dark matter blobs, early halos, you could have this be so powerful that the star can't fully collapse to ignite fusion, and so instead you have a star that's basically held up by dark matter annihilation power. So it's powered by dark matter annihilation, and this is called a dark star. And there are some caveats to this. You need certain models of dark matter to get it to work, but it's a cool idea, and it's one of the things that I'm looking at in my work as well. Is what effect would that have on star formation and galaxy formation and so on. And so that's definitely an aspect of what I'm doing. But part of what I'm doing is trying to put together that kind of idea and also the heating of the intergalactic gas and everything into one model, so that you're not just looking at dark matter annihilation one kind of object, you're looking at it in all the different ways that it can affect the sort of primordial universe, the dark ages and reionization and so on.
Awesome.
Yeah.
Well, I think this is a good place for us to end. Thank you, Adam, for that question. And so what I'm going to do, I'm going to use this new Showcase app. Hopefully it shows up for you guys. So it's also the same way that you guys would be interacting with the Q&A app. So I have put up links to both of our Twitter accounts. So I am at Scientific Scott on Twitter, and Katie is at Astro Katie on Twitter. So somewhere on YouTube, that should be showing up, I think, on the right-hand side of the window if you actually open up the full experience via Hangout. Like I said, in 2 weeks, we'll be getting back together to talk about CMBR, and it's either going to be here on Spaceman News, or we might be moving over to my other project, which is Know the Cosmos. I've been actually... but I will still make sure that it gets shared out to this channel via Google+, since I know that's where a lot of our followers are. We're just making sure that everything gets going to where they go, and these are actually more specific to the Know the Cosmos program. Anyway, so I do want to take time to thank everybody. I see that John Weaver just tweeted at us that he is having morning tea and watching us, so good morning, John. And thank you for all the other comments on YouTube here on Google Plus as well. Thank you, Katie, for again coming back and letting us probe your large brain and and get insights into dark matter. I'm really glad that we're able to have 4 episodes of this. This was really cool.
Yeah, it's fun. Dark matter
really
is awesome.
Dark matter is awesome, and I hope you guys have been able to learn more. I'm sure that we will revisit any specific parts of dark matter, because we have received a lot of questions, and so I will parse through those later on this week to see if there's any specifics that we might want to do a show on. So if there are any questions and you're catching this later, let us know in the comments below over here on YouTube. I won't be checking the Q&A app too much afterwards, but let us know in the comments. Again, hit us up over on Twitter. We love interacting with everyone over there. And yeah, 2 weeks' time. And other projects. And what's up, Katie?
I was just going to say, if you have more questions about dark matter, you can always ask me, of course. You can also check out my website, astrokatie.com, where I post articles and podcasts and videos and things like that I've done, and I've talked about dark matter in a lot of those, so you can see lots of stuff that I've said about dark matter from my website.
Sweet. All right, everyone. Well, thank you again all for watching, for engaging, and for staying with us for a long time. We've been doing this, and I can't wait for our next one to come up. But until next time, thank you again, and keep looking up.
Bye.